Service panels. The main disconnect. All electrical systems require a means of disconnection so that the service can be shut down quickly if any dangerous conditions exist. In this section, we will look at the types of disconnects and the common problems that need to be reported. The service equipment is the necessary equipment, usually consisting of a circuit breaker or switch and fuse and their accessories connected to the load end of service conductors to a house and intended to constitute the main disconnecting means for service. The disconnecting means for service should be located outside or inside the house as close as possible to the point of entrance of the service conductors. The service equipment must be identifiable and marked as a service disconnect. A common service size for a single-family house is 200 amps, and the main 200 amp breaker located at a main panel board would be the main disconnect for the service. Requirements. It is required that the entire electrical supply to the home be able to be shut off with 6 or fewer moves of the hand. This can be in the form of 1 or more knife switches, 1 or more fuses or fuse blocks, and most commonly and in more recently built homes, by throwing the breakers. If the supply cannot be disconnected from one location in this manner, the home inspector should report that the system is in need of repairs or upgrade. Types of disconnect. As discussed, different systems are in common use today depending on the age of the property. Knife switch. This is the oldest type of disconnecting means. We all remember the old horror movies where Dr. Frankenstein was shown energizing his creation. The switches he used were knife switches. Fuse blocks. Often called mains and range panels, the electrical supply is shut down by pulling the 2 fuse blocks from the panel. Breakers. This is the most common type of disconnect we encounter. Throwing 1 or more breakers shuts off the electrical power. In most cases, we see a single main breaker, but there are split bus panels where the homeowner would need to trip several breakers to effect a total shutdown. Again, the rating, or fuse or breaker size, of the disconnect relates to the total amperage available within the home. If the main disconnect is, for example, rated only at 100 amps, it doesn't matter that the SECs are rated for 200 amps. Split bus panels. As discussed, some panels are of a split bus design, which means that the bus bars that the breakers draw power from do not extend right through the panel. Normally, these panels will have multiple double pole breakers at the top of the panel controlling the usual 240-volt circuits, such as for a clothes dryer, stove, and air conditioning unit. However, on these panels, one of these double pole breakers also shuts down power to the lower parts of the bus, which controls the individual 120-volt branch circuits. Remote disconnects. In many homes, and in nearly all mobile or manufactured homes, the service disconnect is not in the main distribution panel. This is not a problem, but care must be taken to fully investigate the grounding and bonding of all downstream distribution panels, as will be covered later. In terms of grounding and bonding, the neutrals and ground should be bonded in this panel only. Notes on mains and sub-panels. Remember that the panel with the main disconnect is the service panel, and panels downstream or on the load side of the service panel are distribution panels. Neutrals and grounds should be bonded together only in the service panel and not in any downstream distribution panels. This will be covered in more detail later. Service amperage. Service. For houses serving one family, the ampacity of the underground service conductors shall be a minimum of 100 amperes, 3-wire. For all other installations, the ungrounded conductors should have an ampacity of at least 60 amperes. The ungrounded service conductors should have an ampacity of at least the size of the load served. Reporting main service disconnects amperage rating. According to the Home Inspector's Standards of Practice, the inspector shall describe the main service disconnects amperage rating if labeled. That is all a home inspector needs to do here. Reporting the disconnect's amperage rating is important for 2 reasons. First, an older home may not have enough power for a modern family's needs. Second, many insurance companies will not insure a property with less than a 100 amp service. As illustrated in the section on meters, electrical services have gotten much bigger since we first started wiring homes for electricity over 100 years ago. When homes were first wired for power, there were few electrical devices available, so a couple of 15-amp lighting circuits and maybe a radiogram outlet were all that was needed. Obviously, in the modern age, we have gotten much more ambitious with our use of electric power. Just about every room in the home has multiple appliances in it, and we need high amperage 240-volt circuits to run systems such as central air conditioning and electric clothes dryers. Development of power needs. The following list is intended to be no more than a rough rule of thumb covering the average unimproved electrical supply over the last century, and would cover the average 1,500 to 2,000 square foot home. 1900s to 1930s, a 30-amp supply. In the 1930s to 1950s, a 60-amp supply. The 1950s to the 1970s, a 100-amp supply. 1970s to the 1980s, a 150-amp supply. And the 1980s to the 2000s, 200-amp supply. Obviously, larger and more expensive homes have always required more power than the norm, and it is not unusual now to see 400-plus amp services in high-end homes. Calculating available amperage. In many cases, the listing information about a home may not be correct regarding the service amperage because brokers or owners rely solely on the size of the main breaker or fuse. Many people are also under the mistaken impression that the total available service amperage is the total of the individual breakers or fuses in the service panel. One way for a home inspector to help communicate the available amperage is to determine the ampacity of the lowest rated or the weakest link of the following components: the service supply, electric meter and socket, service entrance conductors, service disconnect, or distribution panel. Here are a couple of examples. Example number 1, 200 amp service lateral, 200 amp meter and base, 175 amp rated SEC, 150 amp rated panel, 125 amp labeled service disconnect. A home inspector should describe the main service disconnect's amperage rating. Example number 2, 150 amp service drop, 60 amp identified meter and base, 150 amp SEC, 100 amp rated panel, 100 amp labeled service disconnect. A home inspector should describe the main service disconnect's amperage rating. The home inspector may also describe the 60 amp meter as potentially inadequate that should be further evaluated by a licensed electrician. A home inspector is not an electrician. A home inspector must be careful in describing total amperage service supplied to the house. A home inspector must follow the standards of practice and be careful in exceeding those standards. Please refer to the electrical section of the Home Inspector Standards of Practice for more information and details. Inspecting enclosures, Part 1. Electrical panels and boxes, regardless of their purpose, could be inspected for the following safety-related issues. Any deficiencies should be reported as in need of repair or replacement by a licensed electrical contractor. All of the following refer back to the beginning of this course, as they are all related to safety. Panel access, missing knockouts, missing bushings, moisture, rust, signs of arcing, incorrect dead front screws, panel listings or UL ratings, missing legend, damaged breakers, and panel bonding. Panel access. All service panels locations have to provide adequate access for servicing. They should be on a free wall space not less than 30 inches wide, have a clear 36 inches of space in front of them, and have 6 feet and 6 inches of headroom. The panel, though, is not required to be centered in this space. In existing homes with a service of 200 amps or less, a reduction in headroom is permitted by Section 110.26E of the NEC. In older homes, it is also common to find electrical panels inside closets. This is no longer acceptable in new construction. Similarly, service disconnects and remote distribution panels are not allowed in bathrooms. Frequently, the home inspector will see installations that are either restricted by stored items or other systems have been installed in front of the panel. There should be no opening into the panel interior. This is to prevent accidental electrocution by someone being able to put a screwdriver or a finger into the panel and touch a live component. However, inspectors frequently see holes where wiring has been changed or where breakers have been swapped around. All of these should be reported as safety defects with repairs by a licensed professional recommended. It is also common to see upgrades where the old panel has been relegated to the role of a junction box, but all breaker holes are still open. Missing connectors. Anywhere a cable or cable assembly enters a panel or other enclosure, there should be a connector, such as a common clamp connector for clamping down on non-metallic cables. This is designed to do two things. First, to locate the cable securely, called strain relief, and second, to protect the cable from chafing against the enclosure itself. In many cases of homeowner wiring, we will see no connector present at all or an unlisted item being used. Inspecting enclosures, Part 2. Moisture. A crucial point to always bear in mind is that water can be a very good conductor of electricity. Any panel that is damp or wet should not be touched or opened by an inspector. Before even thinking about touching, inspecting, or removing a dead front cover, the inspector should look carefully for signs of water or moisture staining on the panel or on its surrounding wall. As we saw with the service entrance, any failures of the mast or cable entryways may result in water getting into the panel. If there is any evidence of water, the inspector should recommend that the panel be fully evaluated and repaired by an electrical contractor. So delving further into the panel is not only potentially dangerous, it is also unnecessary. It goes without saying that any panel or enclosure showing rust has been exposed to a high level of moisture. It may well be that a previous leak has been repaired, but the inspector should be extremely cautious of inspecting the panel any further. Remember, the inspector's primary goal is to maintain both their own safety and that of their clients. Damaged breakers. There are several issues related to circuit breakers. 1. Are they rated for the model of panel they are installed in? 2. Do they have their handle ties in place on double pole breakers so that both sides of the circuit can be shut off at the same moment? And 3. Are there any signs of arcing, burning, or smoke damage that would indicate that the breaker is not tripping as intended? We will look at these issues in more detail later. Signs of arcing. As part of the initial visual inspection of a panel, the inspector should look closely for any signs of arcing or burn marks on the panel. Again, these may be the result of previously repaired problems, but don't count on it. Also, take a second to listen to the panel, because in many cases, you may hear arcing. Arcing or smoke damage on the outside of the panel is obviously indicative of a previously significant and dangerous condition. It is recommended that the inspector, at a minimum, ask the homeowner for details of the damage and its repair prior to opening the panel. Remember, there are many issues that can lead to this kind of telltale marking, and many of those can lead to the panel board being live or short circuits being caused by removal of the dead front. Inspecting enclosures, Part 3. Incorrect dead front screws. As was discussed for arcing issues, many faults related to damage to conductors inside the panel are caused by either the wrong screws being used or the correct screws running up against the live conductors and causing a dead short against the panel board. The result is that an arc flash vaporizes the steel of the screw-in panel or the copper of the conductor and can send a cloud of molten metal and sparks straight out. That's why the inspector needs to be wearing safety glasses and cotton clothing. Missing legends. All fuse or breaker panels are required to have an accurate listing of what the circuits are connected to. This is properly called a legend. An unsafe condition can easily exist if the homeowner turns off a breaker, believing to have killed the power on the circuit, only to find out that they tripped the wrong breaker. For this reason, Any deficiencies in the labeling of panels should be noted, with the client made aware of the need for this to be rectified. It's more typical, however, that the legend is missing, incomplete, inaccurate, or illegible. Panel ratings. Panels, like any other components, are rated or UL listed by the underwriter's laboratory. Every panel must carry a label explaining where it can be used, what it can be used for, how many circuits it can support, and, most importantly for inspectors, the maximum amperage it can support. In many cases, these panel markings are obscured, but wherever possible, the home inspector should attempt to check the labels to ensure that the panel is rated for the correct amperage. Panel bonding. While looking at general panel conditions, the inspector should pay attention to the requirements for all panels to be bonded to the grounding system. This ensures that any electricity that is imposed onto any metal parts of the electrical system is safely transferred to the grounded conductor, and, in the case of a fault condition, allows the overcurrent protection device to activate properly. In applications where the grounding bus is screwed directly to the panel, this connection is already there. Where the grounds and neutrals, grounded conductors, share a bus, a bond should bridge between that bus and the enclosure. If the ground bus is isolated from the enclosure, for example by an insulated plastic bushing, a bonding jumper needs to be installed between the bus and the metal enclosure. In all cases, look for a green-headed screw, signifying that the panel is bonded to the ground. Fuse panels. Edison base screw fuse panels. These panels were universal from the earliest days of electricity in the home right up to the 1950s, when breaker panels started to appear in residential construction. Many homes built up until the late 1960s still had fuse panels. Fuse panels are generally seen as being more reliable than breaker panels because of the fact that they will always blow when overloaded, either by loads imposed on them or under dead short conditions. Breakers, on the other hand, have been known to not trip at the specified amperages. Many insurance companies, however, will either not insure these homes that still have fuse panels or will insure them at higher premiums. This is not due to any danger from the fuses themselves. Rather, it is indicative of a generally older, unimproved system, which statistically is more likely to produce an electrical fire. Fuse blocks. Many fuse-style panels use a fuse block as both the primary overcurrent protection and also as the disconnecting means. These bakelite blocks contain 2 cartridge or shotgun shell fuses. This block, or blocks, must be pulled to disconnect the power to the home. These fused panels are normally rated at either 60 or 100 amps. Main and range panels. Many homes from the 1930s onward used main and range panels. These have 2 fuse blocks, one acting as the main disconnect and primary overcurrent device, and a second block supplying power for the electric ranges. These became very common from this time on. Some fuse panels may contain as many as 4 fuse blocks, commonly having one as the main disconnect, with the others supplying other 240-volt circuits for appliances such as ranges, air conditioning equipment, clothes dryers, and even other distribution or sub-panels. In all cases, all the blocks must be removed to completely disconnect all the power to the home. Edison base or plug fuses. These are the fuses that screw into many older panels and have the same thread that Edison used for other applications, such as the common light bulb. This obviously creates a problem, since a higher amperage fuse can be screwed into a location supporting lower amperage conductors, effectively turning the conductor into the fuse. Not a great idea. The inspector should recommend the installation of S-type fuses and adapters to ensure that the circuits cannot be overloaded. These adapters screw into the standard fuse location and reduce the thread size down. Various sizes are available, from 15 to 30 amps, and allow only the correct amperage type S fuse to be installed. These adapters are designed so that, once installed, they cannot be removed. They also have the added benefit of stopping someone from repairing a blown fuse by putting a penny under the blown fuse, which is an old practice. It is very common to see overfused circuits on older fuse panel installations. The inspector needs to remember that, in most cases, the installation was designed to supply a relatively small number of circuits with relatively few receptacles. That would have been fine for the average family's needs in the 1950s and 1960s, but that's now exceeded by modern demands. Several types of fuses are available. Some blow very quickly, while others are designed to cope with short, extra startup loads associated with electric motors. These will blow after a short time if the amperage draw does not revert to normal levels. Inspecting fuse panels. As discussed previously, there are two major problems with inspecting older fuse panels. First, check the main fuse amperages. The blocks have to be pulled out, which shuts off all power to the home. The second issue is that these panels tend to be unsuitable for modern, high amperage demands, and they tend to exhibit double taps and overfusing. Pay special attention to the following questions during an inspection. 1. What is the main fuse rating? 2. Are there double taps? 3. Does the rating of the fuse match the conductors? 4. Are the fuses updated to S-type? And 5. Is there any sign of conductors overheating? Breaker panels and breakers. Circuit breaker panels. These are probably the most common type that home inspectors will come across, as they have replaced fuse panels over the last 40 years or so. As we saw for fuse panels, breakers are far from foolproof and require some particular checking. Breaker panels go farther back than many people realize, having been patented in 1910. However, it is unusual to see a residential breaker panel from before World War II. Prior to this, electrical breakers were primarily used in manufacturing and naval applications. Breaker panels started appearing in homes in the mid-1950s in small numbers and were universal in most areas by the late 1960s. As discussed, they did not replace fuses due to any deficiency of the older technology. The problem was that when a fuse blew, one needed to go find a replacement. Breakers are obviously more convenient because when they trip after a fault, they can be reset without replacement. We now have added benefits from circuit breakers with the advent of both GFCI and AFCI protection in many locations. Circuit breakers. Breakers fall into 4 categories, which we'll look at in more detail. 1. 240-volt double breakers. 2. 120-volt single breakers. 3. GFCI breakers. And 4. AFCI breakers. All of these require some specialized knowledge to properly evaluate. Remember, we are talking about energized components. Safety is paramount when investigating electrical panels. Many of our homes now require high voltage and amperage circuits to run appliances such as dryers, air conditioning, stoves, and some load-side distribution panels, etc. Appliances that are 240-volt are fed from 2 120-volt conductors, each connected to a separate bus bar in the distribution panel. It is imperative that when one of the circuits trips due to an overcurrent condition, both conductors are de-energized at the same time. If not, someone could be trying to repair an appliance that is still partially live. For this reason, all breakers supplying 240 volts are required to have the handles tied together by a listed handle tie. Nails, screws, or scraps of wire, for example, are unacceptable. Sometimes the breaker is molded with this connection in place, and sometimes they are linked by a listed handle tie. The inspector should ensure that the tie is present and has not been damaged. A 240-volt circuit breaker also acts as the main disconnecting means in modern panels, disconnecting all the electrical power in the home. Regular 120-volt circuits are fed from one bus bar only. Also in use are tandem breakers, which are 120-volt breakers that feed 2 separate circuits, each controlled by its own handle. These should not be linked. As with fuses, The inspector should ensure that the rating of the breaker does not exceed the rating of the conductors unless allowed by 240.4E or G of the NEC. Otherwise, something other than the breaker is likely to overheat and fail. There are two manufacturers of single-pole 120-volt breakers who have their products listed for 2 conductors. These are made by Square D and Cutler Hammer. These should not be confused with double-tapped breakers, where more than one conductor has been incorrectly connected to a single breaker. Ground fault circuit interrupting breakers are one of the ways to protect circuits and their users from ground faults. Not all circuits are required to have GFCIs, and in many homes, the locations that require this protection have their own GFCI outlets. However, if a GFCI breaker is used, it will provide protection to all receptacles in that branch circuit. GFCI breakers feature trip and reset buttons to ensure that they are working correctly. The inspector should trip the breaker using the test button and ensure that the circuit has indeed been switched off. AFCI breakers. Arc fault circuit interrupters have been required in new construction since the 1999 edition of the NEC. Many jurisdictions are now observing recent code additions, which has expanded the use of AFCI devices to nearly everywhere within a dwelling except the kitchen, bathroom, and most areas where GFCI protection is already required. These breakers are designed to trip if they sense arc faults in the circuits, which are caused primarily by damaged wiring. What is an AFCI? Arc fault circuit interrupters, AFCIs, are special types of electrical receptacles or outlets and circuit breakers designed to detect and respond to potentially dangerous electrical arcs in home branch wiring. As designed, AFCIs function by monitoring the electrical waveform and promptly opening, interrupting the circuit they serve if they detect changes in the wave pattern that are characteristic of a dangerous arc. In addition to the detection of dangerous wave patterns, arcs that may cause fires, AFCIs are also designed to differentiate safe, normal arcs. An example of this arc is when a switch is turned on or a plug is pulled from a receptacle. Very small changes in wave patterns can be detected, recognized, and responded to by AFCIs. A brief history. In the 1999 NEC, these breakers were required only on bedroom receptacles. In the 2002 NEC, they expanded to all 15-amp and 20-amp single-phase 120-volt branch circuit supplying outlets. The 2005 NEC expanded their use to allow AFCI devices similar to GFCI receptacles, but none existed on the market, and their use was limited by 210.12b. Finally, in the 2008 NEC, the use of combination-type AFCIs expanded to 15 and 20-ampere branch circuit supplying outlets installed in a dwelling's unit, family room, dining room, living room, parlor, library, den, bedroom, sunroom, recreation room, and similar rooms, including hallways and closets. Many people confuse the term combination to mean AFCI and GFCI together in a single device. This is partly correct only in that most AFCI devices offer Class B type of GFCI protection, which usually starts at around 20 to 30 milliamps and do not offer any personal protection, as do conventional GFCIs. The combination type AFCIs are designed to activate when there is a parallel arc that reaches a peak of 75 amps. The combination refers to the fact that AFCIs now protect against series arcs as well. They have a 5 amps peak threshold. This is where the term combination comes from. Remember, the term outlet is not interchangeable with receptacle. Outlets are defined by the NEC as a point on the wiring system at which current is taken to supply utilization equipment. Recess lights, smoke alarms, receptacles within outlet boxes, and so on are supplied from outlets. It is likely that many more locations, maybe even the whole house, will be required to have arc fault protection with future code revisions. As with GFCI breakers, these should also be tripped with their test buttons, and the circuit should be checked to make sure it has been shut down. Many early square D AFCI breakers had to be recalled due to manufacturing defects. Currently, however, many AFCI manufacturers are in their 10th plus generation and are proving to be worth every penny when saving lives and property. Inspecting circuit breakers. The inspector should pay special attention to the following questions and report any deficiencies as in need of immediate repair. Does the breaker exceed the capacity of the conductor? Does the breaker have multiple incorrect taps? Do the two 40-volt breakers have their handles tied properly? Do the GFCI breakers test and reset properly? Do the AFCI breakers test and reset properly? Is there any sign of overheating, arcing, or smoke damage on any of the breakers? Problem panels. Panels, types to be aware of. There are several makes of panels whose breakers are no longer available. Also, there are a couple of manufacturers whose panels are known to be problematic. Pushmatic panels. These are still fairly common. The breakers are of a push for on, push again for off design. The issues with these tend to be 1. Lack of panel capacity, 2. Sticking breakers, and/or 3. Difficulty finding replacement parts. While the panel may be in clean condition, the client should be advised that these older panels are fast becoming obsolete as parts are becoming harder to find. Recommend that an upgrade may be in order, as well as a full evaluation by a licensed electrical contractor. Federal Pacific Electrical. The problem with this brand is primarily with their stab lock range of panels and breakers. These featured stamped sheet metal or copper bus bars and breakers with thin copper tabs that were designed to lock into the bus. These have the unfortunate habit of falling out when the dead front is removed, and this has caught many a newer inspector by surprise. Federal Pacific panels were subject to warnings issued by consumer protection groups, which include 1. Loose breakers, 2. Non-tripping breakers, and 3. Arcing problems between the breaker and its bus. The inspector should defer full evaluation of FPE panels to a licensed electrical contractor. Zinsco Sylvania panels. The earliest Zinsco panels had buses made of copper bars and were very reliable. However, during the copper shortages of the mid-1960s, the copper was replaced with anodized aluminum bars. This led to problems of poor contact between the breaker and the bus bar, and many have failed since due to arcing between the components. The problems continued after Zinsco's sale to Sylvania in the 1970s. Due to the frequent failure of the connection between the breaker and its bus, the inspector should recommend full evaluation and possible replacement of the panel. Three-phase panels. Please refer to the three-phase panels diagrams in the How to Perform Residential Electrical Inspections course to see images of the phase concepts. Phased supply and distribution. As discussed earlier in the course, three-phase supply is common in commercial, agricultural, and some apartment properties. Evaluation of these panels is well beyond most home inspections and should be deferred to a specialist commercial electrical contractor. While we are not going to explore in depth the methods of evaluating three-phase supply, some knowledge is useful to the home inspector. As discussed in the service drop section, three-phase supplies have 3 hot or ungrounded conductors, and there may also be a neutral or grounded conductor. Each of these phases or legs carries 120 volts at a different phase from the others. How and from where power is taken in these phased supplies produces different types of supply current. The common services include 120, 240, 208, and 480 volts. In all three-phase panels, the conductors are color-coded to identify which phase they are attached to using black, red, and blue. While there is no required standard of color coding demanded in the NEC, the code does tell us that on a 12208 delta high leg system, the center B, e.g., 208 volts to the ground, should be marked with orange tape to identify it as the high leg. These legs can supply 120 or 240 volts, as one would see in a standard 120-240 volt residential supply. So, it is possible for the average inspector to evaluate some electrical branch circuits in offices or other non-industrial settings, but beware of evaluating the distribution panels themselves. Remember, when in doubt, defer to a licensed electrical contractor. Panel oddities, the weird and the wonderful. The inspector will occasionally see some very unusual panels in the home. Some are now obsolete. Some are just plain dangerous. No panel. 100+ years ago, when we started wiring homes for electricity, there were no standards for panel enclosures. In fact, if an early panel had any kind of enclosure, it was probably built on site from timber and may have had an asbestos liner. Even today, some homeowners will build a distribution center without the benefit and protection of a listed enclosure. Fused neutral panels. For a period in the late 1920s, fused neutral circuits were very common. They were outlawed in 1928 by the NEC. The problem with these is that if the neutral, rather than the live, fuse blows, then the circuit will appear not to be live. However, someone working on the system would easily be able to complete the circuit to ground, providing a return path for the current and thus be electrocuted. Non-metallic panels. As discussed, wood enclosures were very common at one time, but other materials have also been used. In particular, bakelite and other plastics have been used for panel enclosures since the 1940s. They never achieved significant market share, but the inspector may see them on occasion. While plastic panels are rare in residential use, they are very common in automotive and marine applications. Non-rated enclosures. Man's ingenuity never ceases to amaze. Homeowner, quote-unquote, engineers can miss the mark with their ideas on electrical safety. For example, someone might use a tackle box as a solution that, while functional, is still unacceptable. Doorbell transformer. The NEC requires a distinct separation of low-voltage wiring and high-voltage wiring, so you cannot have any part of the low-voltage wires or the transformer inside the electrical panel.